Turns off. Okay, welcome everyone. So today is another Legion day. So I wanted to pick up kind of where we left off from last time, looking at effectively how do we issue um, copies and how do we actually do the analysis, the dependence analysis for copies and tasks and other kinds of things for the logical views. Um, so just to refresh everyone's memory, what we're doing, because it's been a few weeks since the last time we met. So in a prior talk, what we had looked at was we had looked at these copy fill aggregator objects, and actually we can actually take a look at just to refresh everyone's memory about sort of the process, right? So we have physical analyses. They talk to all the equivalent sets. They find all of the copies that they have to do in order copies and fills and other stuff that they have to issue from those equivalent sets to bring the instances that they're trying to map up to date, right? Those all get aggregated in these copy fill aggregators. These copy fill aggregators then have to talk to the actual instance views, which track like all the users, the prior users of those instances, right, to know when it's safe to actually perform copies. Make sure you get all your dependencies right. You're not stomping on earlier writes or reads or stuff like that, right? And then you can actually issue your realm copies and stuff, right? And so we kind of looked at the last time. We started looking at these instance view objects and looking at how they do their dependence analysis to track, what are the prior users on each of the physical instances in memory somewhere that these copy fill aggregators are going to use. And in particular, the last time we looked at the reduction view instance view class, and today we're going to take a look at the materialized view one, which is a little more complicated than the reduction view one, and actually dive into how it does some of the same operations, right? And so tie all this back to the code, page everybody back in, right? Here's our this is the method for copy fill aggregators to issue copies. There's a big extra special case here at the beginning that we looked at, or I mentioned before, but really the main thing we look at are these calls to copy from. Right, so this target right here is a instance view object as well as the source, right? And so effectively you're asking to copy from this target or from this source view to this target view for, with an event precondition and maybe a reduction operator and an expression and some fields, in the copy mask, right? That you're going to issue this copy for, right? And of course, in another talk we actually looked at this, right? And in particular, we were interested in the copy from method for individual views. Just to refresh everyone's memory, where's our hierarchy? Here you go. Right, so this is the type hierarchy for all the different view classes that you can have on instances, right? And in particular, we're mostly down here in this part, which is the most common cases. We haven't looked at deferred views. We haven't looked at collective views. We're probably not going to get to those today. We've looked at reduction views in a prior lecture, and today we're going to be looking at these materialized views over here. And both these are examples of individual views, right? Meaning that they represent only a single physical instance somewhere in memory, right? And they're part of this instance view class, which is effectively instances that actually live in physical memory, whereas these deferred views are sort of like logical views onto things that are not actually materialized in memory anywhere. So we're all the way down here in this part of the type hierarchy for view objects, right? And we looked at reduction views, but we're looking at materialized views, but they both share this common individual view class here. Okay, so we're in individual view, looking at the copy from method, right? And effectively it shows you, this is our source view that we're going to be copying from to copy into this target view, right? We've got our reduction operator ID. We've got an expression of points that we need to copy for. This is the operation that's requesting the copy. This is the region requirement index. We'll ignore this collective match space. That's for collective copies. Doesn't apply to us in this particular case today. Our copy mask, these are the fields we're copying, right? And then we've got some other stuff to help us out with tracing and other stuff. And we can get into some of those later today. In particular, we're going to pay attention, as it says here, there are several cases, but two of them have to do with collective views, so we're going to skip that. We're only going to be interested in this first case here today, right? This is the case where our source is also an individual view, so we're doing a copy from, a single source instance to a single destination instance, right? And, this is actually pretty straightforward. It uses these methods that we looked at. I sort of showed you this interface before, but I'll refresh everyone's memory because it's been a while. we have these common methods on the views that help us find, find preconditions for actually doing the copy, right? So we need to talk to the source view, find all the preconditions for actually doing the reading of that target instance or that source instance before we're actually allowed to copy from it. And we're going to get back an application event that says, this is the event that has to trigger, before it is safe to read this particular source view, right? And you can see here, we say that we're reading. There's no reduction that we're doing here, right? This is our mask of fields that we're doing the copy for. Here's our set of points, right? The operation ID, the index, some apply events and tracing stuff, right? And similarly, down here, let's see. We also need to get the destination precondition actually came up here, right? We also use find copy preconditions on ourself here to get the destination precondition, and so we've got both our source and destination precondition. Right, and at that point we can actually, do the call to issue this copy to Realm, and once we've issued that copy to Realm, we're not going to dive into this today, but we'll probably go look at this in a future lecture. Then we also have to go back and tell each of those views, both the source view as well as ourself, the destination view, here's a new copy user. Here's a new user that's actually using this physical instance to do a copy, right, and record how it's using that instance and pass in this result application event that comes back saying this is the event that'll be triggered when this copy is actually done running, right? And if we actually go look at the instance or the individual view class, right? Let's see, where is find copy? Maybe it's on instance view. Let's see, looking for find copy preconditions. There we go. This is actually in the individual view class, right? And you can see that these are, effectively there's 4 methods here that really help you do all of your kinds of, and I think there's actually, these are probably the main ones for doing copies. Well, actually, the find last users is for tracing, so we can skip that. Initial users from when we start up a new task, so we can skip that one. But really, these 2 methods right here are the two virtual methods, on this individual view class that help you find, the copy preconditions. Then when you're done issuing a copy, it'll actually record the new event, this new done event right here, that will tell you effectively this copy is done, will be done using this instance when this event triggers, right? So, and the last time we did is we actually went and looked at find copy preconditions and add copy user for reduction views. And so today I want to dive into that on materialized views today. And this is going to be a little bit more complicated than the reduction view class. And the reason for that is that we're actually going to try and use a spatial acceleration data structure to help us actually try to, eliminate unnecessary tests on the sets of points in these index-based expressions to actually be able to, figure out, which ones are interfering or overlapping with prior index-based expressions and stuff like that. There's actually going to be an acceleration data structure that helps us out with that. Now, while I'm giving this talk, there's actually going to be a flaw in this design. And so, kind of keep a watch out for it, and we'll see if anyone spots it by the time we get to the end of it. And if not, we'll talk about how we're going to potentially fix it in the future. I was hoping I was going to fix it before we actually gave this lecture, but I ran out of time. So instead, it'll be a learning lesson for everyone to take a look at something that, is maybe not done quite as well as it could be. Okay. So let's actually look at find copy preconditions for Materialized View, right? And remember, Materialized View is a subclass of the individual view. So if we actually look at Materialized View here, right, you can see this. It says here, this is a view that represents a normal physical instance in a specific memory, as you might expect, right? And find copy preconditions has an explicit, not pure virtual method here. So we're actually going to implement this method in this class. Okay, so let's go find that method. We're going to look for Materialized View, find copy preconditions. Okay. All right. So we've looked at this for reduction view. We're looking at for Materialized View now. So it has a very similar structure to the reduction view version of this class. So the first thing is you remember that, from reduction view, we talked about this before, but just to reiterate for everyone, right? Each view object, these Materialized View objects, like all the logical view objects, are distributed collectible objects like we've talked about before, which means there can be multiple copies of them on different nodes, right? But only one node is designated as the owner where we actually do the dependence analysis. And that is frequently the case that is on the same node where the actual instance lives, right? So wherever the instance is in memory, that's where the actual owner node is. But if you have to refer to this materialized view from a remote node, right, you still have a copy of that materialized view object on a remote node, right? It'll just know that it's not the logical owner. And if it's not the logical owner and it gets one of these requests to actually find the copy preconditions, what's it going to do? It's going to turn around and send a message, to the owner node to actually do that analysis, right? And so, in this particular case, there's a bunch of crufty code in here that we're going to need to ignore. Effectively, everywhere you see this enable view replication, you can assume that is off by default. That is sort of a legacy code path that still technically works, but we don't really turn it on for anything. It's actually, has proven to be much slower than other cases. So pretty much ignore everything that you see in these if, def, enable view replications. Mainly what we're going to do is we're going to produce a new result event and return it. So I'm going to scroll down here past this enable view replication stuff because it's not actually on right now. So and you can see it goes all the way down to here, so it has a lot of stuff. So in this case, what we're going to do is if we're not the logical owner, we're going to send a message over to the owner node to actually do the analysis, and we can actually create an event that actually says effectively when it's safe, that the owner node will actually trigger once it's done its own analysis. So we can kind of make an event and return it right away, and keep going on our node, right? Well, meanwhile the owner node will be off asynchronously doing the analysis to figure out what are the copy preconditions and stuff like that. So this will be the event that the owner node will trigger when it receives the message. And we also have to make an event, tracking when we've actually done that analysis to know when that effect has actually been applied. We'll probably talk about the need for that in a future lecture. And then we package up, all of our arguments plus the new ready event and applied event. And then we send off an active message over to the owner node, right, to actually go do that. We record, the applied event in our set of applied events. We record this new ready event, as the result event for ourselves. Again, more view replication here, so you can skip all that part. And then we can return our event right away, effectively saying that, this will be the event that will be triggered, once the owner node does its analysis. When this message actually arrives on the owner node, what it will do is actually turn around and call this exact same method, find copy preconditions, on the object on the owner node. And it'll just trigger that application user event that we made with the result of this method. So that's a pretty trivial thing to do. It'll come right back into this method just on a different, copy of the object on a different node where it's actually the owner. Okay, so that's the case where we have to actually send the message. That's pretty simple. What happens when we actually are on the owner node and we actually need to do this analysis now? Okay, well, there's a few things that we have to get right. So the first thing, there's a few events that we have to consider when we're actually doing this, the analysis to actually use this instance. So the first one, is this start use event. And this comes from the actual underlying physical manager. This event, is really, it doesn't have to do with any tasks or copies or other things using the instance. This is the event that says when it's safe to start using the physical instance itself, right? Because Realm can do deferred allocations, which we've talked about a little bit in the past, right? Like it can create an instance and say, this instance will be ready to use when some event has actually triggered. So you've actually got the name for it, but it's not safe to start using it yet. So that start use event is effectively just the event that says, this is the event corresponding to when Realm has told us it's actually safe to start using the physical instance itself, regardless of any other users, tasks or copies or other stuff that have also recorded themselves as users of this instance, right? So that start use event is there to help us, capture that. So if we've got one, we add it into our set of preconditions that we're gonna trigger. Okay. Next, we make a region use object because it's going to help us actually do the analysis. So, if it's a reading copy, we'll use read-only privileges. If we have a reduction operator, we use reduction privileges. If it's neither of those, then we're doing a writing copy, right? So we can effectively use read-write privileges. And all Legion copies, that are issued by the runtime itself, effectively come with exclusive coherence. There's no relaxed coherence modes for copies that are issued by the runtime itself, right? And if we have, pass in our reduction operator ID. Right, okay, we'll come to what this means in just a minute. But effectively, what we're going to do is inside of this materialized view class, there's going to be a data structure that tracks all of the prior users, of this particular materialized view. And we're going to need to traverse that data structure to find all of the prior users, whether they're copies or tasks or anything like that, that interfere with us. And therefore, we need to record a precondition on them before we're allowed to do this copy that we're trying to do, right? And so this data structure, is this current users member. So let's actually go take a look at that over here in this Materialized View class. Let's see, where is current users? Here it is. And this comment is actually not quite accurate. It's actually not a DAG, but it was at one point, but it is not anymore. So this is an instance of, you see this is a pointer to an ExprView object. And so we can actually go look at that ExprView class here. Okay, and you can see a comment here. An ExprView is a node in a tree of ExprViews for capturing users of a physical instance, right? And so, and this comment is actually accurate. So these ExprViews are going to define a tree data structure. So, each ExprView can actually store, let's see if I scroll down here, can actually store references to a bunch of subviews, right? So you can see there's a field mask set of further ExprViews, effectively defining a tree, where each subview is going to be a subview that represents, I should point out here, each ExprView comes with an index-based expression. So these are a set of points that, effectively record, these are points in an index space, right? That say, this node in this ExprView tree is storing, users that use this set of points. And the way that you have subviews is if an ExprView has a set of points that are completely dominated by your particular view, right? So, I can actually show you a little picture here. So effectively this ExprView, right, like the ExprView at the root of this tree has all the points in the instance, right? So that root ExprView will always contain all the points representing the physical instance. But then if you have users that are maybe only using a subset of that instance, like maybe you're only using the left side or the right or the right side of an instance or something like that, right? Like they will each have an ExprView corresponding to those sets of points, right? And ExprViews live at the same level if they are, effectively non-dominating with each other, right? So the only way to get, a hierarchical aspect of this is if all the points in this ExprView down here are dominated by all the points in this ExprView here, right? So these ExprViews, effectively, they could actually be interfering with each other, right? But since they're at the same level, but neither one of these two would dominate the other, right? And so they can live at the same level, but they are dominated by the one at the root because obviously, this has all the points in the whole instance, right? So you effectively get a tree data structure here that represents, a bounding volume hierarchy where, each of the nodes are nodes where tasks or copies are actually using some subset of points in this data structure. Right, and so in order to find all the interfering things with us, what we're going to do is we're going to start at the root of this data structure, and we're going to traverse down, right, and effectively say, are there any users at this level that I interfere with? If so, we will record them. If not, we're going to go down, we'll record them, and then we're going to traverse down, right, and check each of these guys and see if they intersect with our, set of points that we're trying to do this analysis for this copy, right? Maybe we only intersect with these two ones here, and we don't intersect with this one over here. Right. Then we'll go and traverse. We'll analyze both of these for interfering users, and then we'll traverse down and analyze, this view to see if there are any interfering users for us down there as well. Right. But we'll be able to prune out, having to traverse this subtree over here because it didn't interfere with our set of points that we were analyzing for our particular copy. Right. So effectively, we can do intersections, on these sets of points and see which ones we overlap with, and that allows us to prune out subsets of points. That we might not need to, or subsets of these views that we don't actually need to go talk to because they don't actually overlap with us. Now, I did say, I used to say that this was a DAG, but it's now actually a tree data structure, right? And I actually comment that here. And, I sort of, one of the tricky cases that we used to handle, and I realized that it wasn't worth the complexity of dealing with, is that, it might be the case because these are bounding volume hierarchies, and these two things, let's say these two nodes both overlap with each other, but they don't, neither one dominates the other one in terms of their sets of points, right? Well, it's possible that this ExprView actually is dominated by both of these two things, right? And that would mean that it's actually you could represent this as a DAG, right? Where you actually had, reference from this to this data structure as well, right? But that's actually unnecessary, right? Because if you're going to overlap with this data structure, you're going to traverse down here to this view anyway. There's no need to go down a second path to get here. It doesn't matter, which path you take to get to this view to look for interfering things. As long as you traverse it once, you'll find any interfering users from prior tasks and copies and stuff like that. And then you don't need to, traverse it through a different path. There's no need to actually maintain, this additional edge. Now, you do have to be a little careful here because you can get an unbalanced tree a little bit, where maybe you have lots of dangling ExprViews off of this guy and none over here. So you have to be a little careful with that. That's not actually the fatal flaw that we'll talk about a little bit later, where you could get really perverse performance cases. But it's kind of related. So keep an eye out for that. But yeah, so for the moment, this is only a tree, and we don't try to rebalance or anything. We just maintain, bounding volume hierarchy semantics, where each of these ExprViews are going to track, the users that are using exactly those points on that particular ExprView. Okay, so if I come back over here to this ExprView class here, let's actually look at what are the members we've got on here. Let's see, the other important members, there's not a whole lot in this class other than, there's a lock here. We may or may not talk about this invalid fields class. A bunch of these things are just pointers to things that that we want references to for our context. But the main data structure here are these current epic users and previous epic users, right? And this will look very familiar from earlier discussions in the logical analysis, right? Effectively, this is our to-list set of things where we have our current set of dominating users, right? And then our previous set of users in case we get another thing that doesn't dominate things in the current epic users, and we have to record things from the previous epic users list, right? And that's the same thing that's going on here in this ExprView class, right? Effectively, this is tracking all of the physical users. We can actually go look at this. Let's see if we can find this event field users type def here. I think it is up here. Yeah, here it is. Right, so this event field users type def here is effectively a for every completion event, we have a list of all the physical users associated with that completion event, and you might get multiple ones because you might have multiple region requirements from the same task, right? That all are recording that they're using different sets of fields or whatever on this particular instance, right? So effectively we have a map over all the completion events, right? And then names of all the physical users, and you remember we looked at this physical user class in the prior lecture. And so we're tracking all the fields for each of these physical users associated with this particular completion event, right? And that effectively defines all of the current and previous epic users on each of those nodes in this ExprView tree, right? So now we can actually go back and look at this traversal that actually takes place in this find copy preconditions, right? So effectively one thing you'll notice here is that we're actually going to take a read-only lock on this tree, right? Because effectively, in order to find copy preconditions, we're not actually going to modify this ExprView tree. We're just going to effectively, read over it and look for and read data structures inside of it. We're not actually going to mutate it all. So each of these materialized views has a lock that guards the top of this tree to say that we're not actually going to mutate the shape of this tree. We're just going to be effectively traversing it and looking for overlapping sets of users and stuff like that. And now I can actually explain what this copy dominates does also. So effectively, we have this Boolean condition here, which checks the expression that we're going to be traversing for, and checks to see if it's the same as the the expression for the first node in the tree, right? Because effectively, if you know that your expression that you're traversing for covers the entire node of this tree, then all the nodes that you traverse below, you're also going to cover as well, right? And then you don't actually have to do with all those expensive intersection tests. So as soon as your expression becomes the same as the expression that you're traversing or bigger than the expression that you're traversing, then you don't need to do intersection tests as you're going down. But if the expression that you're testing for is smaller than this expression view expression, then you need to actually do the intersection test to see which subnodes to go traverse and stuff like that. And so this copy dominates Boolean here is just saying, are we testing for all of the points in this node in the expression view tree? And if so, we can do some optimizations. You'll see that, we pass in this copy dominates here into this method, right? And then we'll be able to go take a look at, what we actually dominate, or we can see whether we need to do this intersection test or not. Okay, so this is dispatching on the current users, which is the root of the ExprView tree. So now we can go look at the ExprView class and go look at find copy preconditions. So let's actually go do that. Okay, so here we are. We're on, what we can assume we're in the first root node of the ExprView. We'll see where we recurse down here at the bottom. But we've got our usage for our copy, whether we're reading or writing. We've got our set of points that we're passing in. We've got this like copy dominates, saying whether or not this expression dominates this particular set of points on this node of the ExprView tree. We've got our set of fields that we're doing the analysis for. Here's our operation ID, our index, and some tracing stuff like that. Okay, so as we go to do this traversal, let's see. We're going to want to go look at all of the current preconditions as well as potentially looking at the previous preconditions. So we're going to look at effectively we're going to analyze this node first to look at the users to see which ones we dominate and which ones we don't. Right. So we take again a read-only lock. We're not going to be mutating these lists at all at the moment. We're just kind of sort of like reading over them and seeing which ones our copy is going to interfere with, so we can record any prior users that we're going to interfere with, right? There are two paths here, whether copy dominates, right? If copy dominates, there's no point in testing the intersection of index-based expressions because we know that we already are going to overlap with all the users at this node, so that's going to help us out do an optimization. We'll take a look at that in a minute, right? And if not, we'll go down the other path where we're actually going to have to do those expressions. But in general, in both these paths, we kind of do the same thing, right? So we take a look at the current epic users, and we do this find current preconditions on the current epic users, which means like we look through all the current users and see which ones we interfere with, and we'll go look at that in just a minute. And we'll get back the ones that we'll effectively get back lists of fields for which we saw we observed like some fields, and we also got which fields we didn't dominate on. And then we can compute, this dominated mask, and we use this dominated mask to determine, if there are any fields that we didn't dominate on, then we need to go look at the previous users as well, and that's true in both of these paths. So that's pretty much identical in both cases, whether you're doing the expression test or not. So we'll go look at those in just a minute. I just want to finish going through the rest of this method. One thing we may discover in the process of actually doing these traversals is that some of the prior users have actually completed, their events have triggered and stuff like that. In which case we can actually filter out some of the, if we dominated some of the prior users and we're going to become the new dominated user, we can actually filter, effectively users from the current list back to the previous list. So that's what this little blob of code is doing here. We can also do some filtering, for any, these dead events are effectively, users that have actually had their events triggered, so we can actually filter those out as well. So there's stuff going on there, right? And then here's the recursive part, right? Effectively we say, if we've got subviews and we've got, fields that we overlap on those subviews, right? Then please go through all of these subviews, right? And find, the ones we overlap on fields with. And if the copy dominates, right, well then we're immediately gonna traverse them because we don't have to do any index-based expression tests. But if not, then we'll actually do a test to see if we overlap, and if so, whether that expr overlap now dominates, and then we effectively traverse down the tree on each of those things. And you'll notice that we're actually not holding a lock when we traverse the subview data structure, and it's because we're guarded by that event or that lock, the expression lock that we took at the root of the tree, back in the materialized view, which prevents the tree from changing shape, while we're doing this traversal. So you don't actually have to be holding this view lock. Effectively, there are two locks, one guarding the actual users themselves on each individual node, this view lock, right? But then the subviews are actually protected by the lock, back in the materialized view that guards the shape of the whole tree. So you're kind of protected from that here, right? And then we traverse down the tree, and we come back in this method for the next node down the tree for anything that we overlap with that we need to go traverse. So that's kind of like the generic structure of how we traverse down this expression view tree. Okay, let's actually go take a look at this find current preconditions. Find previous preconditions is going to be very similar, but let's go look at find current preconditions because that's probably the more important one. Okay, there are actually two variants of this method. We're going to look at this one here, which is the one associated. Let's see, is this the right one? This is not the right let's see, there's the right one for copies. There's actually two versions of this. They only differ on a single parameter. In fact, I should probably actually clean them up and make them just one at this point. They used to be very different for reasons that are probably not interesting. But yeah, they're almost identical at this point, and they should probably be refactored to be the same. But we're going to look at this one, which is the one that the copy actually ends up calling. So we've got all of our things that we're trying to analyze for this copy on this node to find any current preconditions. So we're going to iterate over the current epoch users list. There's a special path here. This is effectively this is especially for helping with, actually this is on all the time. This is if not disable legion event pruning. I have a double negative there. Effectively, we can only do this dead event pruning in the case where we're not doing any tracing. So that has to be effectively finding events that have already triggered. Right, you effectively can only do that safely when you're not tracing. It's probably worth a discussion for a future day. But mostly that doesn't impact our analysis here. Effectively, you can say, if we're not tracing, if you find a dead event, you can actually skip it, right? Because it's already triggered. You don't need to record a dependence on it, and you'll be able to prune that out later. Okay, so the next things that we're going to test for, right? The first thing to test for, the easiest thing to test for is testing whether our fields overlap, right? Do any users for this event, have any overlapping fields with us, right? So we can effectively test the summary mask, of this event users for this particular event with a mask that we're testing for, right? And if there's no overlapping fields, well, great, we get to move on to the next event to see, what users might be overlapping. Let's see, I'm gonna skip this comment for here because it's actually a little bit nuanced, but we'll come back to it maybe. Okay, so now that we've established that we're gonna overlap with some of the fields and some of these users, now we can iterate over all the physical users, and we need to test effectively test each of their individual fields, right? Because they might have a subset of fields compared to the summary mask, right? So we do that test, see if there's any overlapping fields there. If there's none there, now we actually need to check the privileges. So we've effectively, by the time we've gotten here, we've established we've got overlapping points, we've got overlapping fields, right? And now we need to check to see if the privileges are overlapping, right? If you've got multiple read-only privileges, then there's not going to be any interference. If there's multiple reduction privileges of the same kind, right, then there's not going to be any overlapping. So we're going to call this has local precondition method. This is actually defined as an inline method. It's a template in the Legion views class. So has local precondition. And in this case, we're actually, effectively this is the template method for actually doing that on the ExprView, right? And you can see this parameter is saying whether or not we're doing this analysis for a copy or not. I really, like I said, really this should be refactored probably into just another parameter. There's not really much benefit in making this a template parameter anymore. The compiler can statically optimize it away, but it doesn't seem worth the benefit of that anymore. There used to be more template parameters in this expression, which is why we did this. And now there's just the one left, and so we can probably optimize it away. But effectively, there's a comment here, effectively saying, so we're comparing two physical users now, right? We've got the physical user associated, that's priorly using this instance. And now we've got this copy that's coming in trying to actually, copy or task really, coming in trying to analyze whether or not it interferes with this prior user, right, based on privileges, right? So we've got this, we've got our usage for our next expression. We've got a set of points that we're analyzing for this next expression, operation ID, the regional requirement index, whether or not the expression covers, right? And then we want another output parameter saying whether or not we dominate, right? So the Boolean return is saying whether we interfere, and then this one will say whether or not we dominate or not. Right, and you can see here, the first thing we're checking here is whether or not, these two users are coming from the same operation, right? If they are, right, and they're coming from different, region requirement indexes, then we don't actually want to return an interference with them because we know that region requirements can't be interfering with each other. So we don't ever want those things to interfere. We always want, copies from later region requirements to bypass users that may have been recorded from earlier region requirements of the same operation. And that's exactly what this case is is filtering out here, right? So that way, if you do your analysis, for one region requirement, and you issue all your copies and record your user, and then some later, copy comes along from a different region requirement of the same user, right? You won't actually end up interfering in that particular case. So that's what this is guarding against right here. right? And then after that, right, the next thing we can do, next simplest thing we can do is to actually check the privileges. And we've actually looked at this check dependence type method here in the past. This is actually, we looked at this in logical analysis because it's exactly the same, and sort of privilege check that we did for logical analysis as well. And what this is doing is checking whether the privileges and coherence modes of the two users interfere with each other, right? And what kind of dependence you're actually going to get, right? And so, it'll do that analysis and say whether you get, one of these different kinds of dependence analyses, right? And effectively, at this point, if you've any of the dependence analyses that are not a true and anti-dependence, we effectively can ignore, right? Atomic and simultaneous coherence dependencies don't matter. These are users on the same physical instance, right? So effectively that'll get handled by some other mechanism, right? But anything that's a true or an anti-dependence, right, then that's going to be problematic and actually be a kind of interference that we need to deal with, right? And then the last most expensive test that we can do is effectively, if it's not the case that either one of these two users covers the expression for this ExprView node in the tree, right, then we actually have to do this expensive test of these sets of points to see whether they actually overlap with each other, right, and see whether they overlap with this particular place, right, and if not, then we can return false. Otherwise, we set dominates to true, and we return that we have recorded an interference here. There's another version of this method has local preconditions called in the previous case, right? It doesn't need this extra dominates parameter here, but it's identical otherwise. So we could probably, again, maybe optimize or refactor this a little bit to clean that up as well too. But in general, they're doing exactly the same thing. Okay, so popping back here, right? So this has local precondition returns this, whether or not we interfered or whether or not we had an interference. If we did, we have to record that, event in the preconditions, right? If we've dominated, then we can go through all the steps to record that we've dominated. We've got, some observed set of fields. We can actually go through and filter out, these events in this particular case, right? Otherwise, if we didn't dominate, right, we have to record that in the non-dominated sets of fields. Right, and so that's what find current preconditions does on this ExprView, and find previous preconditions pretty much does the same thing, except it doesn't have to track all the dominated stuff, and so effectively it's doing a lot of the same work as find current preconditions, just on the previous user list instead of the current user list. Okay, let's see. Before I move on, does anybody have any questions about how we do the analysis on these ExprView objects?
I have some. I have to admit I got a little bit lost. Can you is it easy to describe what the invariants are for the current epoch and for current epoch users and previous epoch users, and and on the high level, when does one migrate from one to the other?
Yeah, it's actually, so these methods or these data structures look more complicated than they are because they're field, right? Effectively, they're over fields, right? So like the simplest way, let's ignore fields. Let's say there's only a single field in this instance, right? In this particular case, you can just have like two lists of users, right? So you have the set of current users and previous users, right? And let's actually ignore fields and expressions. So let's just say that like you've got a flat instance, with like, everybody's always using the full instance. Everybody's using exactly one field. The instance only has one field, right? So in that case, right, effectively, what you need to do is track, effectively two sets of users in order to do dependence analysis, because you need to track, effectively, if you're going to dominate, if you're doing analysis for a new user, right, you only need to track analysis or dependencies on the prior set of users that let's see, I'm not explaining this particularly well. Let me give an example and then it will become clear of exactly what's actually happening here. So let's say you had like a sequence of users of this instance. So let's say you did let's make this T1 does a write, T2 does a read, T3 does a read, T4 does a write, T5 does a write. Okay, so let's actually do the dependence analysis here for these things. So right, so T1 comes along, right? We'll make two lists here. the current and previous, right? And I'm gonna do this in real time, so you guys can see the changes, right? So T1 comes along and it traverses, and says like, okay, I look at the current list of users, right? And effectively it says, there's no users here. I don't record any dependencies, and I'm going to record myself in the current, set of user list, right? So T1 goes in current, right? T2 comes along and it says, okay, I check the current set of users, right? I'm going to interfere with T1 because it's writing and I'm reading, right? And so effectively then I can record myself. I dominated all the things in the current list. So I can bump T1 back to the previous list and record myself in the current list, right? So after T2 does its analysis, the list will look like this, right? Now T3 comes along, right? And T3 says, okay, first I'm going to check the current list, right? And I'm going to check, and I check T3 against T2, and it says, oh, no interference because they're both reading, right? So T3 says, okay, I didn't dominate the current list. I didn't dominate all the users in that list. So I'm going to record myself here because I'm a new user in the current list. But then I need to go traverse the previous list and record a dependence on T1 because like T1, I didn't dominate everything in the current list, which may have dominated the previous list. So therefore I need to record things on the previous list as well, right? So T3 records a dependence on T1 as well, right? Now T4 comes along. T4 says, okay, traverse the current list, look for interferences, right? So it says T2, okay, it's interferes.
Does T3 record a dependence on both T1 and T2?
No. You only record things let's say you traverse the current, the rules are you traverse the current list, right? And you record any dependencies you have on the current list. If you didn't dominate everything in the current list, you have to also traverse the previous list, right? And you can only bump things from the current list back to the previous list if you dominate everything in the current list. Right? Effectively, you're creating epochs.
Two different things.
Yeah, you're effectively creating epochs of things that dominate each other, right? Right. So effectively, you're finding the things everything in the current list has to dominate everything in the previous list, and everything in the previous list dominates everything in the previous epoch that came before it, right? So like, you effectively are creating epochs of things that are non-interfering with each other, but which dominate everything in the previous epoch, right?
But you're only keeping the last two.
You only need to keep the last two because, like, effectively, that that will dominate everything that came even before that, right? So, right, you just don't know whether your new thing is going to go in the newest epoch, or whether it's going to need to record, or whether it's going to start a new epoch, or whether it's going to go in the current one and need to record dependencies on the previous epoch, right? Does it make sense? Right. So T3. Yeah. Good.
Yeah. Just continue the example, and I think I'll probably get it.
Well. So T3, effectively says, okay, I didn't dominate everything in the current epoch. I'm going to be added to the current epoch. Therefore, I need to record stuff on the previous epoch, right? So I record T3 recorder depends on T1, right? Now T4 comes along, right? And T4 says, okay, test against T2, dominate. Right, or interferes, test against T3 interferes, right? Because writes, you can't overwrite reads, right? So T4 overlaps everything, or interferes with everything in the current epoch, right? And so then what you can do is you bump the current epoch back to the previous epoch, right? So this epoch goes away, right? T2 and T3 become the new epoch, or new previous epoch, and then T4 becomes, the current epoch, right? And then, T5 comes along and says, okay, test against the current epoch. It dominates everything in the current epoch, right? That will bump that down. T4 becomes here, and T5 becomes there. Does it make sense? Like what's so effectively,
right.
Like you can notice that these reads can all get grouped together into an epoch, right? Because they're not interfering with each other, but the writes are. I can add some reductions in here if you want some more examples.
I think I understand. Yeah, you will either be appended to the current epoch, or you will make a new epoch.
Or you start a new epoch. Exactly. Which is why you never need to track more than the current and the previous lists. And you can prune things out. As soon as you have something that dominates all the things that came before it on that particular field and expression, right? Then you can effectively prune that out, because anything that comes after you is either going to interfere with something in the current epoch or something in the previous epoch. Right, and anything that was before those two epochs, right, is just post-dominated and will never be touched again, right?
Mm-hmm. So the two checks that you do, you do need to do both a domination
Yeah.
dominates check and
Yes.
a interference check, because interference check tells you when you need to record a dependence.
Yes.
Domination check tells you when you need to start a new epoch.
Yeah, and you need to track domination when you're traversing this current list, right? Because like that's the only thing that will tell you it's safe to start a new epoch, right? When you're traversing the previous list, you're not going to ever change anything. You already know you're adding yourself to the current epoch, and you're recording dependencies against the previous epoch, right? So like, so that helps to like that makes the previous traversal much simpler. But when you're traversing the current epoch, that's when you need to like track that dominance information to know when it's safe to start a new epoch.
Mm-hmm.
Yep.
Okay.
Yep. And the tricky thing about this in Legion, right, is that we're doing all this in a field parallel way, right? Which is why, like, if I come back to the code over here, let's see, like if we look at this find current preconditions, right, you'll notice that like the this non-dominating thing is actually a field mask, right? Because it's actually like a bit, for each one of those fields saying whether it was dominating or not, right? So like, we're effectively recording the fields which are non-dominated in this particular method, and you might dominate on some of the fields but not the other ones, right? And so it's all field parallel, which is why you don't just have like the single Boolean tracking dominance, right? Because each field could be different. There are some cases. There are some cases where like the this. So one interesting thing that could happen is this current epoch list could actually be empty, and that can happen in cases where like if you're actually on this tree, like maybe you're recording a new user up here, right on the root, and you actually like what you can actually do with that is you can actually like filter back the current epoch for the users down, like let's say we're recording a new write up here at the root, that can actually filter down this like as you're doing this analysis on like the subviews down here, right? That can actually means you can actually start a new epoch down here in the subview, but there's not going to be anything in the current list, right? Because like actually the current list is actually stored up here, right, representing the new write that occurred up here that dominated everything in this whole subtree, right? And so like that's what this observed field is tracking here, right? It's actually tracking, did you actually see a user in this this current list down here, right? Because effectively like if you don't actually observe any users for certain fields in the current list, that means that like you can't actually filter and start a new epoch, right? It's most likely that the epoch is managed by something higher up the tree. So that's why we also track this observed field here.
Makes sense.
Yep. So that's the two list trick, right? And it looks complicated because there's like lots of fields and expressions and stuff running around here. But conceptually, that's exactly what's happening. We're figuring out when it's safe to define a new epoch of users and start a new one that we can then filter down. And by just tracking these two sets of users, you can prune out all the old users that are even older than this, right? That you don't even need to test against, even if they haven't triggered yet. So, yep. Okay. Let's see. So we've got about 10 minutes left. So we finished the finding current preconditions. Or we finished find copy preconditions. So if I come back here, right, like if this is back to materialized view, and remember we were all the way down here at the bottom, right? Once you finish traversing your ExprView tree, what you've got is this set of preconditions that you've got, right? And effectively, then it's just a matter of merging those, right, to create effectively the precondition for actually using this this particular view, right? And so that's that's effectively how we find these copy preconditions. Now we didn't actually go look at add copy user yet, but effectively it's going to go try to mutate this tree and actually add the user back into this tree. So we'll have to go look at that probably the next time. But since I've got you here, like, did anybody spot the conceptual problem that exists with the ExprView trees? I'll give you a hint. It does have to do with this picture. Although, like, I sort of hinted at it, but maybe not enough for anyone to pick up on it. give everybody just a few seconds.
Is it that you are there's a hierarchy on the ExprViews, but there's also that is not taken advantage of when you're doing the dominance and intersection tests for the current and past epoch?
Well, we are doing that. Right. If we actually go look at that you're kind of in the right area, but not quite. If we actually go look at has local precondition, we actually do the expression tests down here directly if we have to. But that's kind of orthogonal to this point. We actually we are doing that, but it does have to do with the expressions on these ExprViews that each of these nodes represents. Okay, since Manolis made a good guess, I will go ahead and share the fatal flaw. Right, so the real problem is that right now these ExprViews are actually representing index-based expressions. And the problem with that, right, is effectively that it's really hard to test these index-based expressions for overlapping, because like an index-based expression can actually be like a set of rectangles, right? And I say rectangles, I mean n-dimensional rectangles, right? They're sets of rectilinear objects, right? That's how realm represents these index-based expressions, right? And the problem with that is that you can actually have like lots of these views that are very difficult to test for intersections with each other, right? So if you've got some random expression coming down, through this ExprView tree looking for interferences, right? You've actually got to do those complicated tests on index-based expressions. And in practice, like that can actually get kind of expensive. And Legion does have its memoization stuff for testing those kinds of things. But one thing about instances compared to more general index spaces, right, is that they often occur on rectilinear things themselves, right? Like we kind of have two ways of creating instances in Legion, right? We've got this like, we can make affine instances, which are just nice n-dimensional layouts of sets of points, right? Or we can make compact sparse instances where you've got like a list of rectangles, right, that describe your instance, right? And so it feels like this bounding volume hierarchy really needs to be broken down into like a rectilinear bounding volume hierarchy, which is easier to compress and test against. And then when you test like an index-based expression, you can just test the rectangles in that index-based expression through a rectilinear BVH instead of this like logical BVH, which might have like expressions with lots of separate rectangles. Because like if you've got like an expression that has like lots of rectangles that you're traversing with, and you've got expressions with lots of rectangles in here that you're testing against, it makes it very inefficient to test all those things. To test, you can get like sort of n-squared effects on each of these nodes, when in practice you should be able to do a much better spatial bounding volume hierarchy here to deduplicate those kinds of tests. And so like I think one thing that needs to happen here, and like I said, I'm just hoping to clean this up before giving this talk, but I didn't actually get time to get through it, is to actually like break down these ExprViews instead of using expressions on these nodes, but actually use rectangles and do sets of rectangles, or not sets of rectangles, but make these views represent rectangles, and then maybe have like for each user record different ExprViews for each of the rectangles in the index-based expression for that particular user, and that way we could get rid of like all those expensive index-based intersection tests that we might have to do, and do tests on like rectangle intersection, which is much faster. So anyway, that's the fatal flaw of what exists in here now. Most people don't trip over this. Most people, most users of Legion today are using index-based expressions that are already rectangles, which are actually pretty good, or small sets of rectangles, so they don't hit the really pedantic case where you've got like expressions with lots and lots of rectangles that these things are representing or you're traversing for. But it is something to watch out for, and probably something that should be cleaned up here in the future. So
the point here is to use an approximate at the ExprView level, he would use an approximate
Well,
bounding volume, right?
no. I think I would actually like effectively the bounding. What I would do is it would still be precise. In fact, I want to keep this physical analysis very precise. So what I would do is like when I introduce like let's say you've got like a copy that's using an index-based expression, or copy that's copying a set of points that are represented by several rectangles, right? Then when you put those into the bounding volume hierarchy, you'll put each of those rectangles in, and you'll record the user under each of those rectangles. It'll be precise, but like effectively you blast out the rectangles that actually do represent those index-based expressions, so that when later traversals come through, they'll be able to prune out much more effectively like which when you traverse for other rectangles later, you'll be able to prune out subsets of things to traverse much more efficiently. So, because like when you can actually do when you like the rectangle view of this will actually like you won't end up with whole tons of ExprViews here that might be like intersecting but not overlapping with each other. You'll be able to prune your tree will be much deeper and with less fan out, so you'll be able to prune things out much more efficiently. Yep.
Should I expect that at some point in this traversal, I will always find a node with my exact the exact set of points that I'm touching?
So for precondition testing, no, because like you might be testing for a brand new set of points that no one has ever actually used before. But when you go to add your user, that is what we'll talk about next time. And there is a mechanism for at least for things that are not copies generated by the runtime. There will always be a node, and we'll talk about how we guarantee that has exactly your set of points. But that we'll do next time, because that's a perfect lead into like how you actually do the add copy users and add task users and stuff like that. So we'll do that part in the next lecture. Okay, any other questions for today? All right, cool. We'll see everybody next week. I think I'm gonna try and get Sean to talk next week, but if not, we'll be back and do another Legion meeting. All right, see everybody then.